us consider a scenario where we are pulling on a sled and that sled is going to be dragged across the ground. The strength of our pull is 50 newtons, and even though the sled moves horizontally across the ground from some initial position to some final position, the direction with which we pull the sled is not going to be horizontal. The direction that we pull the sled will be angled up and to the right. So here is the force that we are exerting on our sled. But the sled moves horizontally, so I could draw the displacement of the sled to look something like this. Now, displacement is a vector pointing from the initial position to the final position, and the magnitude of the displacement vector is just the distance that it moved. So in this case, the magnitude of this displacement vector would be 100 meters. To determine the work that we do on the sled as a result of us pulling on the sled, we could say the work done by our pull is equal to the strength of the force of our pull times the distance that the sled moved times the cosine of the angle between the direction of our force and the direction of the displacement vector. Now, in this case, the displacement vector d is entirely horizontally to the right, and the direction of the force with which we pulled the sled is 60 degrees above the horizontal. So I could write the work that we do on the sled as a result of our pull is going to be, the strength of our pull is 50, the distance that the sled is pulled is 100 meters, and the angle between the direction of the force and the direction of the displacement is 60 degrees. So I get cosine of 60. If I put these numbers in a calculator, I get the work that we do on the sled as a result of us pulling on the sled is going to be 2,500 joules. So in other words, as a consequence of us pulling on the sled, we are attempting to give 2,500 joules of energy to the sled. Now, the next part of this question says, if the sled is initially at rest, how fast will it be moving when the sled reaches its final position 100 meters away from its initial position? Hypothetically, if I wanted to, I could treat this problem just like chapter 4 in forces. I could say F net x equals max. I know if I pull the sled to the right, it will accelerate to the right. Now, strictly speaking, if I want to be thorough, I also need to account for the downward pull of gravity acting on the sled. So I would say here's F gravity. I have an upward force on the sled due to the normal force. So I would have the normal force pointing upward. Here's a normal force. And then I would say, okay, the x component of the forces, I'd have 0 from gravity, 0 from the normal force. The x component of the force of my pull would be 50 cosine 60. So I'd have 50 cosine 60. And then I'd have the mass of the sled, which we said is 25. And that would give me the x component of the sled's acceleration. We know the sled is only going to move horizontally. And then I could take this term for acceleration, use an equation from 1D motion to find the final speed of the sled. But we are not going to do the problem this way. We are going to solve this problem using the idea of the work kinetic energy theorem. The work kinetic energy theorem tells us that the net work done on an object, W net, is equal to the change in the object's kinetic energy. Now, what do I mean by W net? The net work done is the sum of the work done by all the forces acting on the object. In this particular example, I have 3 forces acting on the object. I have the force from my pull, the normal force, and the force of gravity. The force from my pull will give or take away energy from the object. In this case, we had a positive number, so the force of my pull will give energy to the object. Presumably, the normal force and the force of gravity might also give or take away energy from this object, and we add up all those works together to find W net. Hypothetically, in a different question, if I had another person pulling, if I had friction, if I had air resistance, I would also need to take into account those factors when determining the net work on the sled. But in this example, I have three forces, so I could say the net work done on the sled here is going to be the work done by my pull, plus the work done by gravity, plus the work done by the normal force, and that's going to be equal to the change in the sled's kinetic energy. Now we already know what the work done from my pull is. My pull gives 2,500 joules of energy to the sled. What about the work done by gravity? I am going to claim that I could look at this problem right now and tell you that the work done by gravity is going to be 0. And similarly, the work done by the normal force in this problem is going to be 0. So I claim both of these terms are equal to 0 in this particular example problem. Now, every example problem, you need to consider it as a unique circumstance. What is my justification for making this claim? Well, in general, I could say the work done is equal to FD cosine theta. And theta right here specifically is the angle between the direction of the force and the direction of the displacement vector. The angle between the force of gravity and the displacement is 90 degrees, and the cosine of 90 is 0. The angle between the normal force and the displacement vector is also 90 degrees, and the cosine of 90 degrees is again 0. So even though I don't know what the strength of the force of gravity is on the sled, I don't know the strength of the normal force on the sled, if I wanted to, I could calculate them, but I don't need to calculate them to answer this part of the question. Because these forces are perpendicular to displacement, I could right away say cosine of 90 is equal to 0, and it doesn't matter what any of those forces are. So all I'm going to be left with for the work kinetic energy theorem is 2,500 is equal to the change in the sled's kinetic energy. So I'm going to now expand out delta KE and write the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And the left-hand side of the work kinetic energy theorem, the total work done on the sled is still 2,500 joules plus 0 plus 0. So I still have 2,500 on the left-hand side. Now within this equation, we were told that the sled is initially at rest. So in this particular problem, I could write V initial is going to be 0, and that gets rid of the initial kinetic energy term. And what I'm left with is 2,500 is equal to 1/2. We were told the mass of the sled is 25, and the final speed of the sled is what we're trying to find, and that will be my VF right there. So I could send this through a calculator and find VF is equal to 14.14 meter per second. If you get comfortable with the idea of the work kinetic energy theorem, using this theorem can make a lot of problems that sometimes can otherwise be pretty tricky or tedious much easier to solve. Now we're going to consider the same problem, but if friction can be accounted for. So in part A and B of this problem, we said we are pulling the sled across the ground, and we assumed that the force of friction between the sled and the ground could be neglected. But what if there is a non-zero friction force acting on the sled? How would that change our problem? So let's say that there is also a force of friction, and we'll set the force of friction to be 10 newtons. This is the magnitude of the friction force. To determine the direction of the friction force, I have to think. Friction always opposes motion. The sled is going to be pulled to the right. Therefore, friction will point to the left. So the force of friction drawn as a vector acting on the sled would look something like this. To determine the work done on the sled by friction, I could say the work done on the sled by friction is equal to the strength of the friction force times the displacement of the sled, basically how far the sled traveled, times the cosine of the angle between the direction of the friction force and the direction of the sled's displacement. So when I plug numbers in, I could say the work done by friction. When I am plugging F and D into the equation for work, the force and the displacement are just the magnitude of these quantities. I assume these quantities are inherently positive and I want the magnitude of these vectors. I do not account for any negative sign yet. So the force of friction in total has a strength of 10 newtons. So I'll have 10 for my force of friction. The total displacement that the sled moves is 100 meters. So I have positive 100 over here. Now we do actually account for the relative direction of these vectors when we plug in an angle for theta. So theta is defined as the angle between the force vector that we are considering and the displacement vector that we are considering. When we considered the angle between the displacement and the force of our pull, the force of our pull was 60 degrees above the horizontal, so the angle that we used was 60 degrees. When we considered the force of gravity and the displacement vector, the angle between the force of gravity and the displacement vector was 90 degrees. In this case, displacement is entirely to the right, the force of friction is entirely to the left, so the angle between these two vectors is 180 degrees. So I would write cosine of 180 right here. As I said, I assume when I am plugging numbers into this equation for work, F is the magnitude of the force, that's an inherently positive number. D is the magnitude of the displacement, that's an inherently positive number. But I account for direction when I plug in this angle. And this angle could change depending on what force I'm considering. If I'm considering the pull, friction, normal, gravity, something else in a more elaborate problem. So if I plug these numbers in a calculator, I find the work done by friction is going to be negative 1,000 joules. I found a negative number for the work done by friction. That suggests that friction is taking energy away from the sled. So what would the final speed of the sled be after it moves 100 meters in this particular scenario? Our technique for finding the final speed of the sled is going to be no different than what we did earlier, only now we have one more term to consider when we calculate W net. So I still have the work kinetic energy theorem just like before. I still have W net equals the change in kinetic energy. Now I have four terms that will contribute to W net. The friction force will do work, the pull that I give will do work, gravity and the normal force also technically contribute to W net. So I could now write the work done by my pull plus the work done by gravity plus the work done by the normal force plus the work done by friction all will add up to the total change in kinetic energy of the sled. For the exact same reasons as we argued earlier in this video, the work done by gravity and the work done by the normal force will both be equal to 0 because the direction of these forces is perpendicular to the direction of the sled's displacement. Now, the work done by my pull is going to be the exact same thing we found earlier. So I have the work done by my pull is 2,500. If I want to be very thorough, I will add 0 for each of these terms. And the work done by friction is like saying I am adding negative 1,000 joules to the sled. So colloquially, I would say I'm taking away 1,000 joules. So I have plus negative 1,000, and that is then equal to the change in the sled's kinetic energy. And I find that in this scenario where we account for friction, the total change in the sled's kinetic energy is going to be 1500 joules. So to find the final speed of the sled, I do everything as I did before. I could say that 1500 is equal to 1/2 mv final squared minus 1/2 mv initial squared. Now, v initial we said was 0 before because the sled initially begins at rest, so that gets rid of this entire term. And then I could say 1500 is equal to 1/2 times the mass of the sled times the final speed of the sled. And when I plug numbers through a calculator, I find the final speed of the sled is going to be 11 meters per second. So as I said before, the way I am interpreting using the work kinetic energy theorem, my pool tries to give 2,500 joules to the sled. So that's like saying I lost 2,500 joules of energy in pulling the sled because I gave that much energy to the sled. The force of friction between the sled and the ground took away 1,000 joules from the sled. So I give 2,500 to the sled loses 1,000 joules from friction. These two forces don't take away or add anything. So in total, the sled gains 1,500 joules of energy. If I know how many joules of energy the sled gained, then if I know the initial speed of the sled, I could learn something about the final speed of the sled. And that's just what we've done here.